Hi, this is Laur Hesse-Fischer of the MIT Environmental Solutions Initiative, and you're listening to Today I Learned Climate. Last week, we learned all about methane. It's carbon dioxide's more powerful cousin and the second biggest contributor to climate change. Today, we're looking at another class of greenhouse gases that, whether you know it or not, you're probably using in your home right now. And while they're pretty rare compared to methane or carbon dioxide, the world is on track to make a lot more of them in the years to come. I'm talking about refrigerants. You might know them already by the brand name Freon.
Refrigerants are in every refrigerator and freezer in your home. The refrigerants are also in the air conditioners in your home, either the window air conditioner or the big compressor that sits outside. And if they leak those refrigerants, they get into the atmosphere, and that's a potent greenhouse gas. My name is Ronald Prinn, and I'm a professor in the Department of Earth, Atmospheric and Planetary Sciences at MIT.
I asked Professor Prinn to join the show because he's an expert in the physics and chemistry of our climate system, and for decades has been leading a project to track the levels of refrigerants in the atmosphere. But before we get to what these gases are doing on our planet, let's talk about what they're doing in our homes.
A refrigerant is a fluid that can go from the liquid phase to the vapor phase and backwards and forwards, and in doing so can take heat out of one part of the system and give it out to another part.
How does this work? Well, these chemicals were engineered in a lab so that they boil at really low temperatures, like often way below 0 degrees Fahrenheit. And when things boil, they absorb heat from around them. So if you have a chemical that boils at a super low temperature, you can absorb heat even in a place where it's already quite cold, like, say, inside of a refrigerator. Refrigerants run through pipes in your fridge, soaking up heat. By running that warm gas through something called a compressor, we can turn it back into a liquid, at which point it's really, really hot. That extra heat then gets blown out into the air, which is why the back of a refrigerator is quite warm. And around the refrigerant goes, absorbing heat and then releasing it.
That was a big breakthrough in the 1930s to find a non-toxic chemical compounds that could be used as refrigerants in this new application. And it became critically important to refrigerators and air conditioners.
Refrigerators and freezers have been key to feeding the almost 8 billion people on our planet and for storing medicine. Air conditioners use basically the same technology, using refrigerants to take heat from inside your home and move it outside. Those, too, have been a boon to human life. Air conditioning saves lives during heat waves. In fact, they're growing even more important as climate change brings us more dangerous extreme heat. The International Energy Agency expects the number of air conditioners to more than triple by 2050 as more people are lifted out of poverty and can afford air conditioning. All of these advances were made possible by the invention of the first major refrigerants, a group of chemicals called chlorofluorocarbons, or CFCs. But just like the abundant energy from coal and oil has come with a cost, these refrigerants come with a cost too.
In the 1970s, there was a discovery that the chlorofluorocarbons, when they are leaked to the atmosphere, catalytically destroy ozone.
Yep, I'm talking about the hole in the ozone layer. But wait, what does the ozone hole have to do with climate change? The short answer is, it doesn't, really. But bear with me, because we're circling back to climate, and we're going to learn something about solving big environmental problems along the way. So ozone is a naturally occurring gas in our atmosphere that absorbs ultraviolet light before that light reaches the surface of our planet. Without it, we'd get way too much ultraviolet radiation, enough to cause a lot more cancers, damage plants, and cause a whole lot of other problems for life on Earth. And chlorine, the first C in CFC, rips apart ozone.
And it became very important, therefore, to prevent further emissions of the chlorofluorocarbons into the atmosphere.
So do you know what happened? The whole world got together and banned these ozone-depleting refrigerants. Every country in the United Nations, every one, signed on to something called the Montreal Protocol, setting a date to stop making CFCs forever.
The Montreal Protocol was a landmark piece of environmental policy. It was enacted in 1987, and within about 10, 15 years, it stimulated the phase out of the chlorofluorocarbons and their replacement by less dangerous chemicals to the ozone layer called hydrochlorofluorocarbons and hydrofluorocarbons, the latter ones containing no chlorine at all.
It's really the perfect story of world leaders coming together to solve an urgent crisis for our planet. But at the same time, we were starting to replace CFCs with the chlorine-free HFCs. We were also learning about the other big problem brewing in our atmosphere, climate change.
It was in the 1980s that various scientific studies were concluding that the chlorofluorocarbons were also potent greenhouse gases, as were the hydrochlorofluorocarbons and the hydrofluorocarbons that replace them. They have a large warming potential. 1 ton of one of these gases is equivalent to thousands of tons of carbon dioxide.
Why are they so powerful? Well, if you've listened to the last 2 episodes of this show, and I actually highly recommend that you do to understand some of what's next, you know that there are 2 things that can make a greenhouse gas particularly powerful. The first is if it has lots of atomic bonds that catch heat energy before it can escape into space. And the second is if it lasts a long time in the atmosphere. The refrigerants that we use today check both boxes and have another special trick besides.
They are potent because many of them last for thousands of years in the atmosphere, but they are more potent even because they absorb in regions of the infrared spectrum of the planet that carbon dioxide and water vapor do not absorb.
Infrared radiation, which is how Earth sheds heat into space, spans a long range of wavelengths. Greenhouse gases like carbon dioxide and even water vapor can capture radiation at some of those wavelengths. But at some other wavelengths, there's no natural molecule that's good at absorbing it.
These are called atmospheric windows, clear regions where infrared radiation can escape to space. So purely synthetic greenhouse gases are dirtying the window, if you like. They're filling in the gaps. Remember, these are purely synthetic chemical compounds, whereas carbon dioxide, methane, nitrous oxide, the big 3 greenhouse gases, are naturally occurring. And that means their molecular structure is very different. And that is a major reason why they are equivalent to hundreds or even thousands of tons of carbon dioxide.
These are just incredibly powerful greenhouse gases. Okay, so I'm looking now at a listing online for a 12-ounce can of a refrigerant called HFC 134A, which you'd use to recharge an AC system. It's the size of a can of soda. If I bought that can and just opened it up, those 12 ounces would cause as much warming as half a ton of CO2. That's like driving 1,300 miles in a gas-powered car. Taken together, refrigerants, even though they're pretty rare in our atmosphere, have caused more than 10% of the warming that our planet has experienced to date. And unlike our CO2 emissions, which are slowly starting to level off, refrigerant emissions are still rising fast as more of the world gets wealthier and buys air conditioning and refrigeration. So, what do we do about all this? well, these compounds aren't doing any harm while they're inside our refrigerators and air conditioners. But the issue is if they break or if they're not carefully disposed of.
Usually when they're dropped into the dump, they will end up leaking, and there are still a lot of chlorofluorocarbons stored in waste dumps around the world in old refrigerator units, and ultimately they become leaking out of the waste dumps as well.
So one opportunity to stop some leaks is to stop throwing our refrigerators and our air conditioners into landfills.
If you have a refrigerator with a refrigerant in it, it would be illegal to throw it into the waste dump. You would have to have it recycled. A technician would come to your home, plug into the plumbing system, and suck it all out.
At which point the refrigerants themselves could be recycled or destroyed. And we can also make an effort to do this with all the old appliances that are today hanging out in landfills. For the refrigerants already out there in the world, this is about the best that we can do. Looking ahead, though, there is another option.
Just don't manufacture these dangerous chemicals. You don't get, obviously, leakages if you're not manufacturing them at all. The best is to replace them with new, less dangerous chemical compounds. The ones that have the least impact on global warming among these synthetic fluorinated gases are the shorter-lived ones. The shorter their lifetime, then the less damaging they'll be.
So just like we once phased out CFCs, today we're looking to phase out HFCs. What we replace them with will probably be another greenhouse gas. The leading candidates are called hydrofluoroethers, or HFEs, and hydrofluoroolefins, HFOs.
They're on the market, and we can measure some of them in the atmosphere already. So we know they're there.
But although these are also greenhouse gases, they are much less powerful because they break down in the atmosphere quickly instead of staying there for hundreds or thousands of years like CFCs, HFCs, and carbon dioxide. It's a step in the right direction. The good news is that this is a step the world is already taking. In 2016, the Montreal Protocol that banned CFCs was amended to slowly also phase out the long-lived HFCs. And most of the world has signed on to that too. And with good replacements waiting, this transition could go just as well as the original Montreal Protocol did. Because today, while the world is struggling to make strong enough targets to ramp down greenhouse gas emissions, and to meet those targets and to make sure every country is on board, it's helpful to remember that this kind of worldwide environmental cooperation really is possible. We've done it before. That's our show today. We have links in our show notes to more resources on refrigerants and an educator guide with some classroom activities to help you learn more. You can find all of that at tilclimate.mit.edu. TIL Climate is produced by the MIT Environmental Solutions Initiative at the Massachusetts Institute of Technology. David Lishansky is our editor and producer. Aaron Krol is our associate producer, scriptwriter, and did our artwork. Michelle Harris is our fact checker. Sylvia Scharf is our climate education specialist. Ilana Hirschfeld is our production assistant. The music is by Blue Dot Sessions, and I'm your host and producer, Laur Hesse Fisher. Thank you to Dr. Ronald Prinn for joining us, and thank you for listening.